Alright, here's our Module 1 review. We're going to go through everything that we learned in Module 1. So starting with Topic 1, which was rigid motion, so that's reflection, translations, rotations, things like that. So, number 1. Translate triangle ABC 3 units horizontally. Label the image A prime, B prime, C prime. How are the values in the ordered pair affected by the translation? So if I look at where each point is, a big thing that happens that's incorrect is a lot of people will put 3 spaces and then draw the triangle, but that's not how it is. Each point gets moved 3 spaces. And it didn't specify which direction, we'll just say to the right. So A is moving 3 spaces to the right, so there will be A prime. C is moving 3 spaces to the right, there's C prime, and B is moving 3 spaces to the right as well. And there's B prime. Okay. So how are the values of the ordered pair affected? So it's asking really just about the coordinates. So if I look at A is at -6, 7, and A prime is at -3, 7. And of course we could go through this with each one, but they're going to change in a very similar way. So the y didn't change, but the x did. And that makes sense because all we did was we slid it to the right, which is a change on the x-axis. So x increased by 3, which makes sense because we moved it over 3 units. Number 2, rotate the triangle PQRS 90 degrees clockwise around the origin. How do the ordered pairs change? If you don't have patty paper, because most of us don't just have that at home, there's some other things you can do. So if I look at the fact that I'm trying to rotate it around this point right here, 90 degrees clockwise, if I physically move my page, then it's going to give me an idea of what this looks like. So 90 degrees would be like that. So pretty much when I change this position, when I change the shape, then I'm going to have one point that's over the edge, and then it'll go over 3, up 3 to get to the next one. So it'll be up 2, over 1 for the first point, and then over 3, up 3 from there. So let's go back. Up 2, over 1, that'll be S prime, and then from there over 1, 2, 3, up 3 is going to be P prime. And once you have like some of the spots, you can just go from there. So like the fact that Q, if you look over, turn it again, it's going to be over 4, up 3, over 4, up 3, and then if I look at R is, when I rotate it, just over 1. Just like that. Okay, so let's look at how the coordinates changed. If I look at S is -2, -1. And if I look at S prime, it is over -1, up 2. I think I see something happening here. There seems to be a switching of numbers, but let's do one more just to see if that holds true. So let's do, I don't know, P. So P was over -5, up 2, and P prime is over 2 and +5. Okay, so now we can definitely see a pattern. So y became x, and x became y, but not just became y, became positive. Like that. So the -x became the positive y. Number 3, reflect the parallelogram over the the y-axis. How do the orders pairs change? So the y-axis is this one right here. So everything's just getting flipped over. Everything's mirrored. So J was 1 over, so it'll be 1 over this way. There's not going to be any moving up or down, just flipping over. I is over 3, so it'll be over 3 this way. H is over 8, so we'll go over 8 over here. G was over 4, so we'll go over 4 over here. There we go, something like that. So now let's see how the coordinates changed. If I look at J, J went from being -1, -1, to being +1, -1. Okay, so maybe it's something like the Y didn't change, but the X did. Let's do one more just to check that. Let's do G. G was +4, +5. G prime was a -4, but +5. Okay, so it looks like the Y doesn't change, but the X becomes it becomes opposite essentially. If it was negative, it becomes positive. If it becomes positive, it becomes negative. Because that makes sense, because all we did was we flipped it over. So it went to the other side of the X timeline essentially, this whole number line here. So X became opposite. Okay. Whereas if we flipped it over the X-axis, then X wouldn't change and the Y would become opposite. Number 4, Henry draws the triangle, then translates the triangle to create F prime, G prime, H prime. The distance from F to F prime is 4 centimeters. What's the length from G to G prime? So they don't tell us how far everything got moved, but the fact that like F to F prime is 4 centimeters leads me to believe everything got moved 4 centimeters. So, I mean, we don't know what this looks like, but if it's like F, G, H, and it got moved, and this is F prime, and this is 4, then this should be 4 as well. So G to G prime should be 4 centimeters, because it's one of the things that stays consistent. Here on number 5, it's asking which of these elephants is congruent to this one right here. So remember, congruent means the same. So, but not every single little part is the same. The orientation doesn't need to be the same, that's the way it's facing, but it needs to have the same like lengths and angles and just the same size. It can be rotated, it can be reflected, it can be pointing in a different direction, any of those. Congruent just means like it's the same elephant essentially. Now, patty paper would be the easiest way, tracing it, just overlaying it, but there's a couple other things you can do. If you just have, anything that you can use for a measurement tool, so like maybe I'm going to take a pen and say, okay, well from the trunk to the back legs is that far, and so I'm going to go over to all the others and see if the trunk to the back legs is that far as well. So like this one, okay, that's the same length. That's not the same length. That's the same length. That's not the same length. So pretty much like you could use measurements, even just your fingers if you think you can hold it pretty steady, to see like if the height stays the same, stuff like that. So it doesn't need to be patty paper, you just need to somehow confirm that all the sizes and angles and stuff like that are the same. So pretty much we saw that 1 and 4 were congruent and 3 and 2 are not congruent. And I know that looks pretty obvious when you're just looking at it, but I mean, if this was like 2% smaller, you wouldn't be able to tell that just from looking at it. So patty paper, of course, is the best really to confirm, but you can just do some informal measurements as well. Moving on to topic 2, which is similarity. So in the last topic, we were really talking about congruency, which means everything's the same. With similarity, it means things are proportional. So if I make a scale model of something, everything's proportional, but of course it's not the same thing. So number 1 says triangle EFG is dilated with a scale factor of 1/2 to create E prime, F prime, G prime. What's the measure of the angle of the measure of angle F prime is 36. What's the measure of angle F? So if we know some things about similarity, we know that angles don't change. If I make a really big angle here and a really small angle here, they're both still right angles. So angles don't change with scale, like the lengths and stuff like that will, but angles won't. So if f prime is 36 degrees, f is going to be 36 degrees. Number 2, dilate triangle fun using the origin as the center of dilation and a scale factor of a half to form f prime, u prime, n prime. So since it's a scale factor of a half, that means everything's getting half the size, but it's also closing in half the distance to the center. So that's going to make this really easy to do. So like n is at 6, so it's going to shrink in to be at 3. So there's n prime. F's a little bit trickier since it's at a diagonal, so we can kind of use like the parts of it. So it's over 2, so instead it'll be over 1, and it was up 4, so instead it'll be over 2, or sorry, over 1 up 2. So like right there. Same with u. Let's see, it was over 6 down 4, so it'll be over 3 down 2 instead. Just like that. Okay. Did the shape get bigger or smaller? Definitely smaller. It's half the size. How did the coordinates change? Well, like n went from 6, 0 to 3, 0. F went from, let's see, -2, 4. So it looks like everything kind of got cut in half. All of them were like divided by 2. And what's the relationship between the original and the dilated one? Well, obviously they're not congruent because they're not the same size, but they are proportional to each other, which we call similar. And if you don't remember, the symbol for that is like just a squiggle line. All right, moving on to number 3. Which one of these is similar to the original butterfly? Now this one is not as easy to do as the elephant one because we're not looking for the exact same thing. We're looking for it to be proportional. So you can kind of give like an eye on this, like C is definitely not because it looks stretched out. So we're looking for ones that look proportional. So you can't just do informal like looking like this because that's not what we're looking for. We're looking that it looks to see like the same except maybe bigger or smaller, not stretched out, everything kept the same. So A and B do look like those are similar. And we could check angles on this, so maybe we check the angle of this wing and make sure it's the same angle of the other ones. On to number 4, dilate triangle ABC on the point, no, that's bad grammar, using the point C, so that's this one right here, as the center. So you don't always need to use the origin, and a scale factor of 3. So everything's getting 3 times farther away from C. Now, C, though, is not going to change because it can't get 3 times farther from itself. So C prime is the same as C. B, don't look at the coordinates because those don't matter right now. You can kind of ignore any coordinates. B is 2 spaces away from C, so instead it needs to be 6 spaces away. It's right there. So there's B prime. A is 3 spaces away, so it needs to become 9 spaces away. 6, 9. So there you go. Okay. 5. Describe a sequence's transformation that exists that exhibits the similarity between the pair of figures shown. So there's definitely a dilation that's happened. It's gotten bigger, but it's also been moved. And in fact, it looks like it got reflected. It's not just, it didn't get rotated. If it was rotated, then A would be over here, so it has to be reflected. Now there's a couple options. It could have been reflected and then dilated, or it could have been dilated and then reflected. And either one actually works. You just need to be really specific if you're taking a test or something like that. Now this is informal, so I'm not going to be super specific with these. So maybe I want to say it got dilated first. Normally I would need to find the center of dilation, but we can settle for just finding the scale factor. So if I'm looking at the fact that like D to A is 2 and then D prime A prime is 4, well, definitely got 2 times bigger. So a scale factor of 2, and then after that it got reflected across the y-axis. but it could have easily have been reflected first and then dilated. Number 6, given that TOP is similar to MAN, what's the measurement of PT? So these are proportional. That's what similar means. So in the way that 11 is proportional to 5.5, we're wondering what this distance here. So if I know the scale factor, so 11 to 5.5 is a half, so this is going to be the same scale factor. So I need half of 8.5, which is 4.25. And that's inches. Okay, finally we are on topic 3, which was all about just different angle relationships and lines and triangles and stuff like that. So starting with number 1, solve for x. So we have a 30, and an unknown. So something we need to remember is all internal angles of a triangle add up to 180. So if that's true, and here we have 30 and 30, so that's 60, the rest of that 180 has to be 120. So if you know the other ones, you can always find that third one. Same thing on number 2, I have a 22, I have a 104, so that's a 126, so if I take that away from the 180, the rest should be our x. And of course you can use a calculator for this, just like that. Alright, 3 is on the same principle. So I am only given one angle here, this 48. So knowing also that straight lines are 180, if I know this is 180 right here, then this side right here, this angle is going to be the rest of that 180. So 180 minus 48 is 132. Like this is 132, but then this straight line right here also makes up 180. So this is, and some of you saw this right away, so this is how you get those opposite internal angles like that, where they're going to be the same. So this is 48 as well. So if we know 48 plus x is 180, we can solve for that. And I put 2x because there's 2 x's. So this is now just a solving for unknown. So I would take that 180 and I would subtract 48. Which we already found was that 132. And so 2x's is 132, so whatever half of 132 is going to be our x, and that is 66. So that means each of these angles are 66 degrees. Number 4. Okay, this looks like there's a lot going on, but let's just start with what we know. So we just want to find some missing angles. So let's ignore this small triangle, just focus on this big triangle for now. So we have a 31, an 82, and this angle is going to be the rest of that 180. So if I add up 31 and 82, that's 113. So if I take that away from 180, that's going to be this one. So 180 minus 113, and that's 67. So this angle right here is 67 degrees. But there's other angles we can find too. Using the same principle we found over here, if this is 31, this right here is also 31. And then once we have that, now we have 2 of the angles and we can find the third one. So we have a 67 and a 31. So that's 98, and I need to take that away from 180. Because that's going to give me what this angle is, since it makes up the rest of that 180, and that's 82. So this right here is 82 degrees. Alright, number 5. Are these triangles similar? How do you know? So triangles are similar if they have all 3 angles the same. But we kind of just saw that if you know two angles, then you know the third. So it's actually not really true that you need all three. You actually only need two angles. That's the kind of cool thing. So if we have two similar angles, if two same angles, the triangles are the same. So we have this tiny triangle that's inside this big triangle. So we just need two same angles. Well, this angle of T is definitely going to be the same as itself. So that's one. And then I'm seeing here's a 34 and here's a 34. Well, 34 is the same as 34. And of course we could find these ones, but it doesn't matter. We already have two similar angles. So they are similar. Which means they're proportional, obviously not congruent. Number 6. Okay, this fancy stuff right here is saying that L1 is parallel to L2. The parallel lines in the middle is just the shortcut for that. So if the measure of angle 8 is 49, which is this one right here, what are the other 7 angles? So that seems like a lot, but remember, straight lines are 180, so let's just start there. So if 8 and 7 is a straight line, they're going to add up to 180. So if 8 is 49, I just need to subtract that from 180. And that is 131. And I know that doesn't make sense because obviously angle 7 looks smaller, but most of the time these are never drawn to scale. They're just going to give you an angle. So don't worry about that. But it also means you can't just grab a protractor and measure these. So in the same way that this was a straight line, this is a straight line too. So 8 and 5 are going to make up 180, and so it's going to be the same as 7. And same way this way. Okay? And you can also see you have that opposite angle aspect going on as well. So we've got all of these lower ones done, but what about these ones up here? Well, doesn't all of this look the same as that? And I know I said normally ignore what it looks like, but they told us that L1 and L2 are parallel, which means that the situation here is going to be the same as the situation up here. So all these angles are going to be the same as the angles up here. So whatever we've got going on here, we can just put those same things in the same spot. So like lower right corner, upper right corner, and such.